Okay, so we will now prove this lemma. So let us start the proof. Consider the following set. A, it is defined to be the set of all elements in the ring R that look like this: RA plus SB, where R and S are arbitrary ring elements. Okay, now we will first show that this A is actually an ideal. It is clear that A is non-empty because we are considering, it's just clear. You choose any R and S from R, you will get one element in A. So that makes A non-empty. So we know that, and we are not going to mention that, although that is necessary for before we try to verify that A is an ideal. Non-emptiness is necessary. So let us first show that A is a subgroup of R under addition. Let R1A plus S1B and R2A plus S2B belong to A. This automatically means that R1, S1, R2, S2, these are elements in R. Then we calculate their difference. R1A plus S1B minus R2A plus S2B. Using the elementary properties that are true in a ring, in a general ring, we can write this like this: R1 minus R2, using all the associative law, distributive law, all those things. And you can clearly see that this element also has the same form, and so this belongs to A. Hence A is a subgroup of R under addition. Also, for any R belonging to R, we then have to verify the second condition for an ideal. So we are going to do that now. For any R belonging to R, we have R times R1A plus S1B is equal to, ultimately this can be written as R1A plus RS1B. So this also has the required form for it to be in A, so it belongs to A. Note that we have shown that any ring element times any element in A again belongs to A. Usually this is not enough to decide that A is an ideal. We need to also verify it from the other way, changing the order. But since we are working in a commutative ring, so we don't have to bother about those things. So A is an ideal of R. Okay. Now since we know that we are in a Euclidean ring, and in a Euclidean ring we always have a unit element, and at the same time there is one more condition, that at least one of A or B is non-zero. So using this information we can show that the ideal A is actually a non-zero ideal. It's not the zero ideal. Since it's already given, assume without loss of generality that among A and B, A is non-zero. Then A can be written as 1A plus 0B, where 1 and 0 are playing the role of R and S here. Okay, and the fact that 1 is there in the ring, that we have already proved as that corollary to theorem 371. So this has the required form again, so it belongs to A. Which shows that you can you can justify the existence of 1 by writing it follows from the corollary to theorem 371. I am not writing that here. Okay, it's understood. Which shows that A is not the zero ideal. Now, by theorem 371, now we invoke the result that every ideal in a Euclidean ring is a principal ideal, but at the same time our ideal is non-zero. So that means it will be generated by a non-zero element. There exists an element D not equal to 0 in A such that A is generated by D. A is the principal ideal generated by D. We will now show that this D is actually a greatest common divisor of A and B. Okay, since D belongs to A, so according to the definition of A, D will also be of this form for some R and S, which we will take to be lambda and mu respectively. Since D belongs to A, D is equal to lambda A plus mu B for some lambda and mu belonging to R. Okay. Now we have already seen that A belongs to A, likewise B also belongs to B, but let us just write it for the sake of uniformity. Let's once more write 1A plus 0B and B is equal to 0A plus 1B, both belong to A. Now note that since A is the principal ideal generated by D, that means every element of A is divisible by D. D divides every element of A. So in particular, D will also divide A and B. Thus, D divides A and D divides B. Note that D being non-zero is essential here, because in these divisibility relations the divisor can never be 0 by definition. So that's why we needed to make sure that A is a non-zero ideal, and because of that we need the condition that at least one of A or B is non-zero, which the author failed to mention. So that is a small mistake. Okay, so thus D divides A and D divides B. Now so this is one of the conditions for D to be a greatest common divisor of A and B. The other is that if there is any other common divisor, then that divides D. So that we will now verify. Now let C belong to R such that C divides A and C divides B. So automatically we know that C is a non-zero element, and C divides A and C divides B. That is, C is a common divisor. Then by the remarks on divisibility we have this: C divides lambda A plus mu B, and that is nothing but D. So that tells us that D is the greatest common divisor of A and B. Moreover, D has the required form. Okay, D appears as a linear combination of A and B with coefficients coming from the ring. This shows keep in mind, I am again mentioning this fact that this can have many different values. This is one of the values. Okay, because we have not proved anything about uniqueness of D. Such a thing is in general not there. The fact that we get a unique greatest common divisor in the ring of integers for two given integers, at least one of which is non-zero, it's because we have restricted the GCD to be a positive integer. Okay, but without that restriction, the negative of the GCD is also a GCD. Why that happens we will see. Okay, let us now proceed with what we have here. For now we just take it as a fact that since we have not proved that this is unique, we have only proved that it exists. So that's why this only this proves only the existence of GCD, not its uniqueness. So here the proof ends. Okay, so the next definition is that of a unit element. No, not unit element, unit. Let R be a commutative ring with unit element. An element A belonging to R is said to be a unit in R if there exists some element B in R such that AB is equal to 1. That is, an element in R is said to be a unit if it has a multiplicative inverse. Okay, it has an inverse with respect to multiplication. A word of caution: do not confuse a unit with unit element. A is a unit and 1 is a unit element. Okay, they are two different things, although 1 itself is also a unit, because 1 times 1 is 1, so that is always there. A unit is an element which has a multiplicative inverse in the ring. An example is, a simple example is this: in the ring of integers there are precisely two units, -1 and 1. It's because -1 times -1 is 1, and 1 is always, if there is a unit element, that is always a unit. No other integer is a unit. Okay, that's because if you try to take the so-called reciprocal of an integer other than 1 and -1, then that is not an integer, it becomes a rational number. For example, if you try to take the multiplicative inverse of 2, then it becomes 1 by 2, so that is not an integer. Now these units actually are the things that determine how many greatest common divisors we will have for two given elements in a Euclidean ring. That's why I said that the traditional GCD of two integers, since it has been decided that it will be positive, so that's why we get only one GCD. If you leave that restriction, if you relax that restriction, then you will get the negative of that also as a GCD. What I am trying to say here is that if you find one GCD, multiply that by the units in the ring, you get other GCDs. Why they are GCD, I leave that to you. Okay, so that means if D is one GCD and U is a unit, you try to reason that UD is also a GCD of that same two elements A and B. You look at the definition of GCD and try to show that UD is also a GCD. Okay, so we now move on. Now there are some lemmas regarding this unit and some other things. So this is lemma, this is the second lemma. So what it says, let R be an integral domain with unit element. Let A and B be two elements in R such that A divides B and at the same time B divides A. That automatically tells us that both A and B are non-zero. Okay, then B is equal to UA for some unit U in R. So if this happens, then B is equal to UA for some unit U in R. You can see that we have, if you recall, we have proved a similar thing for integers. If A and B are two integers and we have both of these divisibility relations to be true, then we have proved that A is equal to plus or minus B. So you can see that in place of U here we have plus 1 and minus 1, which are the two available units in the ring of integers. So that's the thing. In general we have this, and the proof is not very difficult, it's rather easy. Most of the results and the proofs we are seeing here, they follow the same pattern that we have come across when we proved similar results for integers. Okay, so now we are in a more general setting of Euclidean rings. Integers is one example. Okay, so since A divides B and B divides A, so we directly use the definition of divisibility. So here B will be a multiple of A. Let B equal to RA, and or let us write like this: B is equal to UA, or we can confuse that U with this one, right? Let us use RA, and this one tells us that A is also a multiple of B. So A is equal to SB for some elements R and S belonging to R. We don't yet know the nature of R and S. They are just, as of now, they are just elements in R. So you can see that we can replace A with SB in this equation. Then B is equal to RA, which is equal to RSB, and this can be written as RS times B. Now note that we are in an integral domain with unit element, and because B divides A, B is non-zero. So from both sides of this equation we can cancel B out. Since R is an integral domain, if you recall, in an integral domain we have the cancellation loss. Integral domain and B is non-zero, the equation B equal to RS B implies 1 is equal to RS. Note one more thing, looking at this, we are in an integral domain and B is non-zero. We may be tempted to cancel B out in every case wherever this type of equation appears, but keep in mind that it is given that R is not only an integral domain but it also has a unit element. So unless that is mentioned, we cannot cancel B, because then we will be left with nothing. No? If there is no unit element, then we cannot cancel it, because for to be able to cancel from both sides, we have to be able to write this B as 1 times B, and then we can cancel. Okay, so now we have 1 is equal to RS. So that automatically tells us that R is a unit, or yes, R and S both are units. This implies but we only need the uniqueness of R. This implies R is a unit. And we have B is equal to RA. And that ends the proof. Now looking at this equation, it seems like we can define a relation between any two elements in such a ring, calling them to be related if they are connected by an equation of this form where one of them is a multiple of the other by a unit, and such a relation exists, and it is we express this by saying that A and B are associates. So that is the next definition. It just creates a language of saying that this equation holds, that between A and B there is a relation like this. It just says that. So let R be a commutative ring with unit element. Two elements A and B belonging to R are said to be associates if B is equal to UA for some unit U belonging to R. You can also write A equal to UB. Nothing will change because this relation turns out to be an equivalence relation. In fact, that is the next remark. And that is one of the exercises that we will prove at the end of this section. The relation of being associates is an equivalence relation. And that is exercise 1. At the end of the section. It's very easy to prove. And the thing that we were saying, although I left it to you to show that if we multiply a GCD by a unit element, by a unit, then we all get another GCD, but we will have to prove that. So you don't have that homework. Okay, now we will do it as exercise 2, and that is the next remark. Note that in a Euclidean ring, any two greatest common divisors of two given elements are associates. So this tells us that once we have a greatest common divisor, by multiplying it by all the units we can generate we can create the other GCDs, and this is exercise 2. So this is not left to you to solve, we will do it here, and after this we are now going to state and prove one lemma which uses the first condition of a Euclidean ring. You may remember that in the definition of a Euclidean ring there are two conditions. The first condition has an inequality that looks like this, and the second condition is the one, of course, which gives us a version of the Euclidean algorithm itself. Note that whatever we have done so far, we haven't used this. So now in this new lemma we are going to use this first condition. This lemma basically tells us that if we multiply an element in a Euclidean ring by a non-unit element, then its d value goes up. As we take more and more non-unit elements and multiply them with the given element, the d value becomes more and more. So that's the lemma. So this is the third lemma. So exactly the lemma asks this. Okay, so let R be a Euclidean ring let A and B be two non-zero elements in R. Both of them are non-zero, such that B is also a non-unit. That means B is not only non-zero, it's also not a unit. Then the d value of A is strictly less than the d value of AB. Okay, so that's what we want to prove now. And the proof goes like this. I mean, again, we are going to use the first theorem that every ideal is a principal ideal, and then along with that we will use the first condition for a Euclidean ring. So let me just see, I seem to have forgotten the proof. I did it long ago now. So we first considered the ideal. Okay. So consider the ideal A, which is the ideal generated by the element A, principal ideal generated by A. From the proof of Theorem 371, we know that d of A is, or I can phrase it like this, A has the minimum D value among all the elements in capital A. Okay. So A has the minimum D value among all the elements in capital A. Since AB belongs to, okay, okay, so what I was going to write here is that DA is less than or equal to DAB, but for that I don't need to say these things. It's because I am getting that from the first condition itself. Okay, so after considering this ideal, the proof won't go like this. From the definition of a Euclidean ring